Hello, afternoon. Welcome back after the lunch. I must say I was here a bit earlier and somehow I mixed up the beginning of the session and I thought it's 1:30 and the room was almost empty and I thought, oh my God, nobody is coming to this session. So I'm very pleased that quite a few people are here and it's the right time to start. This is one of a few grid sessions we have in the conference. I'm happy that we have them, and this one I hope will be very interesting. We will address several grid issues, looking into applications as very demanding things in the network, but also about the European Grid Initiative and other things. So, three interesting speakers, three interesting topics, and I would like to welcome the first speaker, Ludek Matiska from Czech Republic. He's a very busy person. I'm glad he made it to Bruges. Last week he was in Spain. So Ludek is working for Masaryk University and for CESNET, and I believe he will tell you the rest. So please, the floor is yours.
Yeah. Thank you for the introduction. I am here to tell you something about the European Grid Initiative design study. I hope that you didn't have too many opportunities yet to hear some of the lectures which were given, especially by Dieter Kranzmiller, the coordinator of this European project, and some other people from the project about this scope, and I hope that I will be able to present it here at the networking community. So, with the grids, where we are currently at the moment. In fact, we are at the moment where the scientific communities, at least some of them, are using large-scale grids on a regular basis, and many other small communities, in fact, are using grid technologies, even if not using the grid infrastructure themselves, but the grid technologies to start and collaborate, to start deep collaboration among themselves, either on a very large scale or in some smaller setup in smaller communities. So, we also see some interest in industry, where industry is interested both in providing the infrastructure, contributing to the middleware development, and also, naturally, to find other ways how to sell the grid idea and the grid concept to their own customers. So what we have now is a situation when the grids are there, the grid technology is available, but this creates a kind of dependability on the technology and grid themselves. So, especially for those communities that are looking for long-term use of grids, we need some long-term sustainable solution. And this is exactly the goal of the European Grid Initiative. The European Commission is also aware of the fact that the large-scale grids are currently supported and funded by rather short-term projects. The largest European project in grids, and in fact the largest project globally, the Egi, the Enabling Grids for E-Science, has a two-term project period. Now we just started this month the third phase, and there are hopes that there will be a fourth phase. So again, we need some solution what to do when to overcome the problem of the two-year terms for the grid infrastructure. And I'm just using this citation to show that even the EU at the highest level is aware of the need to find a different approach how to make grid infrastructure more sustainable. Here is just an example of the largest, as I said, European grid infrastructure, and in fact global, because you see many sites using the same technology and connected to the same grid infrastructure in Latin America, in Asia, and there are in red projects which are somehow at least trying to find interoperability. It means availability or ability to move jobs between the infrastructures. The Open Science Grid and other activities in the US and Naragi in Japan. Yeah, pardon, that was only here you see the picture, and in white you see the projects funded by European Union which use the common infrastructure and the common middleware for grids. This we will skip. And then, as I said, we try to find a way how to make grid sustainable, and this is done within the scope of what we call European Grid Initiative. What are the main purposes of this? It's to define and find ways to create sustainable grid or European e-infrastructure. This may have even higher goals than just grids as a computing resources or data resources there. The idea is to do this through the coordination of national grid initiatives and national grid infrastructures. So it's based on the idea that every country within Europe and elsewhere has some kind of infrastructure, and that we need to have some kind of coordination and integration of these. And the EGI, the European Grid Initiative, is trying to find conditions and organizational basis for somebody which will take care of a production and shared research infrastructure in Europe and hopefully elsewhere. Here, just as a picture of many projects, both at national level on top and international, EU-funded within Europe and going also outside Europe, to demonstrate that there is increased push of activities which are looking for some kind of sustainability, and we see there the future through the European e-infrastructure as a solution, and naturally other evolution of individual projects on especially national basis and on international in areas where the shared infrastructure may not provide the services we are looking for. Oh, fine. Yeah, that's... Don't know. Yeah, that's fine. It just takes a little bit more. This is a picture which demonstrates that, in fact, the whole Europe currently is somehow involved. As you see, the green will eventually cover the whole Europe, with the exception of very few states like Andorra, Vatican, and I think Luxembourg. So all other states, and also we see some European, not European Union states, like Russia, Ukraine, and Belarus, who are also involved and participating in the European Grid Initiative to look for the sustainable future. Here we see also some projects, okay, and. So, to really create the initiative, the European Grid Initiative Design Study European Projects has been prepared and accepted and launched. It was submitted to the infrastructure calls last year, and it was approved, and as we will see, it started on September the 1st. The goal of this design study project is not to create the infrastructure itself, but exactly to define the conditions, how to get to the sustainable infrastructure. So, to provide a conceptual setup and operation of a new organizational model for a sustainable pan-European grid or even e-infrastructure, and also somehow to be in touch with all national grid initiatives or similar bodies in every country to really get a wide approval and wide support for the results of the project. As I said, it started on September the 1st. The idea is that it will last 27 months, which is more or less overlapping the end, or going, that's incorrect. It's up to 2010, because it's to overlap the end of EG3 to make sure that EG3 is taken over by some new organization. Here we see the members. The EGI design study team is rather small, because this is just a core team which works with the help and support of representatives of all the NGIs, of all the national grid initiatives. We see that the team somehow covers the Europe and also covers large countries, Germany, UK, Italy, France, and smaller countries, Greece, Czech Republic, Austria, and also has a DFN, so there's a networking part. In fact, 3 partners are national research and educational network providers, GRNet, DFN, and CESNet, to make sure that there is also a strong correlation with the ideas and visions of the NRENs themselves. EGI, the acronym, as I said, the European Grid Initiative is really an initiative to find a way how to create sustainable grid. But EGI is also the organization which doesn't exist yet, but which is one of the expected results of the design study, the proposal and eventual setup of such an organization at European level, not a national one. And this Egi organization is expected to take over from all the individual European projects like EGE, like DESA, like all the other, and probably even more, which I shown on the picture at the beginning, to really get to the situation when it is the organization that coordinates grids through Europe. But it will not, the idea is that this is not the organization which will own some substantial resources or really provide the services on itself, but that all this will be done through coordination and through the national grid infrastructures. And I will use the EGI both to represent the initiative and most often to represent this organization plus the NGIs, which will really execute the grid of the future. When I spoke about national grid initiatives, the idea is here to use very similar pattern to the one which we know from networking. That national grid initiative is some recognized national body. It may or may not have a legal, it may or may not be a legal entity, but it is a recognized national body with a single point of contact. So that there is really just one organization, or at the end one person, who is able to represent the country on discussions and especially on political and technical decisions at the European level. And that this NGI is able to mobilize national funding and resources for the grid, for the infrastructure, and it is also able to operate somehow the national infrastructure. It not means definitely that it owns the infrastructure. In some cases it may, in some cases it may not. It may be similar to the EGI at European level to really get the coordination at the national level and below. And naturally should do things like support not only operation but support of user communities and somehow to make sure that the user communities in the country are really properly served. The idea is that the EGI and NGI will work in a complementary base, in a federated approach, and the responsibilities to find out what is NGI, what belongs to NGI, and what is the EGI task is exactly the purpose of the design study. This is just that the EGI design study has few work packages which initially started with the requirement collections. Then what is now in a peak is the functionality definition, and I will speak it in the second half of the presentation. And there is the legal issues, because when we think about establishing somebody, we have to deal with what is possible and what not from the legal point and organizational point of view. And then there is the WP5, which is the work package, which is expected to work in the second half of the design study project to take what is prepared during the first phase, the first half of the project, and then really make sure that it will happen. The idea is that around between June and September, we will get the approval or we will get the general consensus at the European level of the ideas which we are working on, and then the WP5 will take over and will really start to implement them. Any formal signature process, any less formal and more technical steps which will be needed to have something in place at the moment when EG3 will end or other related projects to EG3 will end. And there is naturally a promotion and dissemination work package as is usual in any EU project. Here is the chronology. What is interesting for us are the two workshops. One which happened last year during the Egi 07 conference, and the second which happened just a few months ago in Rome in March. The workshop in Budapest last year, the idea of this workshop was to present the project and to present the requirement collection and the first analysis. We started to collect use cases on the grid use, on middleware development, on application requirements, and to make sure that analyzing them, we really understand what the communities, both the people who own the resources and are willing to provide them, and the communities which we expect to use them or are already using them say, within Egi framework, what they really are looking for, what they are, where they are satisfied with the current solution and what they would like to see in the future, especially if the really pan-European infrastructure will emerge. So this is just a picture from there. The more important was the Rome workshop. And I will, in fact, discuss more in detail about this, because this was the workshop where, again, all the NGIs, practically all the NGIs were represented, and some of NGIs sent up to 2 other experts from their own country to participate in the discussions and to get us feedback. And the Rome workshop was there to present the different aspects of the future of the sustainable infrastructure, what we call the functions of EGI, to the community and to get the first feedback. So we presented there something about grid operations, something about user-oriented functions, legal structures, management, and the middleware. And all what was presented were drafts as a base for discussion. And in fact, I will present some basic ideas of these drafts here. Here is a picture from the Rome. And now let's go to the individual aspects. The grid operations. When EGI design study was conceived, there were few key assumptions about what we are looking for. And the 2 key assumptions are the continuity requirement and the functionality requirement. The continuity says there are already large-scale grid infrastructures operated as projects within Europe. And we don't want to stop these at the end of their project and then to start from scratch with a completely different infrastructure. So we would like to see some, as seamless as possible, transition from the current state to the future. It's not completely possible. There will be some changes, but the idea is to keep these changes as small and as non-disruptive as possible. And the second is functionality requirement, which relates to the first one, that the functions offered, at least at the beginning of the EGI operations, will not change dramatically from those which are offered now. This is especially, both requirements came especially from the high energy physics community, because their Large Hadron Collider will start this year, in fact, almost in this moment, and they will have a huge amount of data in the year 2010. And they don't want to get into the situation when they have the large collider running and they don't have the grid infrastructure being able to process all the data, or stopping to process, say, for several months, and they have to relearn everything from scratch. But there are also other communities who expect to be in the year 2010 in a situation when this gap or interruption or disruption will be too drastic for them. So there was a discussion. What is the EGI operation? There are 2 extreme views. One is large-scale production grid infrastructure built on national grids that interoperate seamlessly at many levels, not just on one, say, sending jobs there and back again, and that they are able to support a wide range of applications, from those who have a really strict deadlines, strict security requirements, and so on, and to those who simply use this grid kind of a scavenger infrastructure, where they are happy to use what is left after all the other, when they don't have any specific strong requirements. All the other extreme, this is one. The other extreme is a loosely coupled federation of NGIs, where each NGI or even part of NGI is completely free to run and operate whatever they would like to have, however, and then there is interoperability at some very fuzzy defined way. Like, yes, we are able sometimes to submit jobs from there, but we lose all the information what happened with the jobs because we don't have the monitoring Europe-wide, we don't have the security, so if you would like to send it elsewhere, you lose everything because you have no idea what will happen when it crosses the boundaries between these loosely coupled grid islands. Naturally, because there is a strong backing of EGE and communities behind it, the idea and the input for EGI design study was to focus on the first one, this large-scale infrastructure. However, most people, in fact, behave like the second one, the loosely coupled federations, are the right solution for the grids. So currently, and we will see what will happen in June, there is a kind of a serious problem when trying to define the roadmap for the future, because it's not clearly, I mean, the initial input was clear that we would like to get to the seamless operated infrastructure. But the actual behavior of people, and when they are presented with the implication of this, they behave differently, and again asking the questions whether we really would like to manage the operations, so to really be able to say you will run this and you will do that, or just coordinate, saying yes, if you do that, it may perhaps work, but you are free to do whatever you would like, and if it doesn't work, okay, it doesn't matter. Is there a common middleware? That's another issue. If there is something which we can run everywhere, or whether each island will take whatever he likes, or whatever it's developing, and then we will try and we will see what interoperates, what doesn't, and if it doesn't, again, is really anybody who cares there or not? And what does interoperability mean? As I mentioned, for us, interoperability is at many levels. For many people, the interoperability is really at the level of I'm able to send my job there and eventually get the results, and I don't care about anything else. And I have no strict requirements on the stability, on the security, and which may be acceptable for some users and may be completely unacceptable for the rest. So currently, we focus on the first, the seamless integration, and there, in the Rome workshop, we presented a multi-level operational model, which is a model which defines a set of services. This is still under preparation, that must be operated on a coherent way, which really means the EGI will kind of dictate to national grid initiatives what they must run. They must do other things in parallel with this, but there will be some services which must be available for the national grid infrastructure to become a part of the European-wide. Naturally, the responsibilities are at NGIs, but the EGI can say you are not fulfilling your responsibilities, what you are expected to do, so you will not be part of the club. The proposal in Rome was that there will be support for multiple middleware stacks. I will get into this when I will touch the middleware, but the problem was, or the outcome of the Rome workshop was, that this was not accepted in general by the community, by the NGIs. They were looking more into a more specific, I would say more authoritative approach, which will tell them you have to run this, this and that, and you will get support for this and that, and it will cost you that. But if we say that there are 3 middleware stacks, that there are options and opportunities, then it's very difficult at the national level to decide whether we again have to run all 3, just one of them, and which one of them. And what if we would like to run just one of them because we don't have more manpower, but there is one tiny community within the country which is collaborating with people who use the second one. And we don't have manpower enough to support seriously 2 different stacks. So this is the operation. Naturally, there are user-defined functions which are less controversial, because there was kind of an agreement, general agreement, that the grids must also include some application support based on support centers and activities at the national level, and that the international level will only take care of coordination and a seamless transition of the know-how and knowledge, but that the actual support is done nationally, which is more or less agreed by all and expected by all or most of the national grid initiative representatives. The training, again, there may be some smaller countries who are not interested in running their own T infrastructure, but everyone is interested in some training of the users and also training of people who run the infrastructure. So there is, again, nothing controversial in the proposal to somehow coordinate and interconnect the training infrastructures through Europe and, again, exchange the know-how and information. And naturally, dissemination, making sure that even new scientists are aware of the potential of European grid infrastructure. There is a last, apart from the middleware, the management. We started because we are kind of expected to propose the way how the EGI will be set up as an organization, to also speak about the management. The idea was that the EGI is not running any resources. They are owned and run by the national grid initiatives or their partners within the countries, so that the EGI can be a lightweight schema. Doesn't have to run thousands and thousands of CPUs with all the overhead associated with this. So mainly coordination and planning, and if there are some services which must be guaranteed at the European level, they will mostly be outsourced. Like within Egi, we have a global system for tracking the user requests, and the idea is that the similar, which is run by currently in Karlsruhe, and the idea is that this may be a solution for the sustainable future as well, that they will run this on behalf of EGI for the whole EGI community. So the EGI will be responsible for coordination and also making sure that everything is going smoothly, including the money. Both, there may be some money, hopefully from the EU and from the national grid initiatives, to put together and make sure that this really converge, that the NGIs are not behaving like child on a playground going to completely divergent areas. There is a proposal management structure with some EGI council, which is the top body representative of every one country, of every one NGI, which is associated to this, and there is just a director and the usual staff, and the idea is that there will be three main divisions, three main responsibilities: the technical, the administration, and the operations. I know, I will skip this. And the last from this are the legal structures. There was a lot of discussions whether we can use the experience again from networks with a Dante, or whether a completely different setup should be used. The outcome is still not completely clear, but it will be, say, again, not controversial, not too much controversial. There will be some kind of a bid who is willing to host such an institution, but the idea is that there will be some kind of a legal body which will encompass all the NGIs. And the last thing which I would like to touch before the end is the middleware. The problem is that there is no grid without a middleware. If you don't have something which will glue all the resources together, you cannot glue them. But the problem is that there is no one middleware solution globally or even within Europe. In Europe, we have three major stacks, three major streams of development of middleware. There's G-Lite, which is within Egi project and related projects, the ARC, which is used mostly, but not only, by the Nordic countries, and which is in many aspects similar to G-Lite. They in fact have common roots, but in some aspects they diverge in a way how they implement some services. And there is a Unicore, which was originally developed to create a grid of IBM supercomputers, and then extend it to cover more systems, but it's still more supercomputer oriented than the classical cluster and almost desktop computing of the Egi or G-Lite and ARC target structures. And there are open questions there. Who will develop the middleware? Will this be a responsibility of EGI or elsewhere? And who will pay for it? Will this go through EGI or not? What and where to converge, and what would be left independent? So are we able to find a unique shared solution for middleware within Europe, which is something which the NGIs are pushing for, because they would like, from their point of view and the point of operations, it's much easier to have one thing to operate, to run, to train people for. But from the application point of view, this may not be the case. They are willing to have a flexibility, to have a plethora of solutions, but this is almost impossible to run in parallel currently on a shared infrastructure. So whether we really converge to something and how we will achieve the convergence. And what will be the interaction between middleware development and EGI. And this is kind of a provocative question, whether we really do need shared common middleware and shared common infrastructure. Whether we are not in fact happy with these islands, which returns back to the discussion of operations. As I said, the EGI design study works with the assumption of the shared infrastructure. But it's good to keep in mind that there are other options, and we have to agree on one thing before we really commit ourselves to start to pay, to start you to support us also financially. Because if we take the wrong direction, we may face serious problems rather early on, because the application people will leave the system unused and in fact will start to oppose it. So this is the overview. I will skip it. This is something which I already said, the definition of Egi Organization. The idea is that the definitions will be provided by the Egi design study and then evolved gradually. And just to see, okay, there are also in Rome we presented some resource estimation which were not accepted as they were proposed, which were just a simple accounting. We said, okay, we would like to run this, and we need at least 2 persons there, at least 3 persons there, and so on. And at the end, we ended with 82 FTEs, which is not a light schema for EGI operation. And even 155 FTEs for the middleware development. This includes everything, G-Lite, ARC, Unicore, and even things going, say, in direction of Globus. So this was not accepted, but it was presented there, and it gives a rough estimate of the real manpower which will be necessary. It doesn't mean that everything will have to be paid directly, but more or less this manpower, and even much higher, will be needed at European level to really make these things happen. And the last, I think 2 slides, are the schedule. You see that the 2009 was incorrect. It was still 2010. And you see the overlap with EG3 and the idea that in May 2010, we have this EGI grid operational. If there will be such a thing, it must happen at that moment. And there are some. And the last thing which I will mention is that in Geneva, at the end of June and the beginning of July, there will be the 3rd of the Egi workshops, and this will be the presentation of draft papers. The presentation where we hope to have proposals for all the questions which I presented here and which were discussed last time in Rome and which are now very heavily and extensively discussed within the project itself. And the idea is that we will be able to present a coherent proposal how to proceed further and with what. And so we are at the end of the presentation. The Egi organization is proposed to become a glue between various grid communities in Europe and outside. The Egi design study works on definition of required mechanism and functions, but it is based on the assumption that the requirement is to create a shared infrastructure like we have a shared networks. If this is not true, the Egi design study is going in a not completely correct direction. So we are trying to define ways toward a single shared sustainable environment for scientific communities, for their everyday work, but there is still some doubts in some science communities whether this is really the future the science wants. And that's the end of my presentation. Thank you very much.
Okay, we have time for 1-2 questions. Anything from the audience?
Everything is clear?
I was listening and thinking, well, it's quite clear what we should where we should be at 2010, but there are still very many questions how to get there and if we will get there in time and so on and so forth. So thank you very much for this interesting insight in the future of grid developments in Europe.
We will see more in June and at the end of
yes,
the
so
workshop,
we are
what will be the reaction and what will be the final, the final, at that moment, proposals from the, because I didn't want to now to put here some of the discussions which we have inside, because it's sometimes diverging, sometimes converging, and it's really inside the project. But I will be here if anybody is interested.
Yeah, if you think you know how the future should be shaped, then talk with the presenter. Thank you.
Yeah. Thank you very much.
Okay, now I would like to invite the second speaker of our session, Ralph Koning. Ralph is from the Netherlands, and he finished his master's degree last year in the University of Amsterdam. And now he's working in the University of Amsterdam with Nortel Networks on the Cinegrid project. So, Ralph, he will talk about the grid content transmission on layer 2 engineered paths. So I'll give the floor to you.
Thank you. Well, I'm Ralph Koning. I'm doing a project for the SNA group and Nortel. Okay. Yeah. Sorry. I'm doing a project with Nortel about PBT and Cinegrid on layer 2 networks. Well, the main question is, can we use layer 2 Ethernet techniques like PBT for building a high-quality media network that protects the media experience? Now, well, what do we mean by media experience? If you're watching, for example, a live stream on the internet and the network connection gets hooked up with other kinds of traffic, you notice frame drops or glitches in the stream. If you want to take this to, for example, cinemas, you don't want this. People pay for the movies, and frame drops and glitches are things you don't want to see. Good. The mission of Cinegrid is to build an interdisciplinary community that's focused on research, development, and a demonstration of network collaborative tools to enable the production, use, and exchange of very high-quality digital media over photonic networks. We at the UVA do research on networks, and we have photonic networks also, and we are building an exchange for Cinegrid. This is a map of GLIF. GLIF is an international network. It connects NRANs together and scientific institutions. And Cinegrid uses this network to distribute its content to various locations in the world. Well, high-quality video. At this time, you have HD TV in your home. You can buy an HD TV. That's the lowest quality we use. The stream uncompressed is about 1.3 gigabit per second. And as you can see, the difference between 720p and 1080p doesn't differ that much in bandwidth terms, because the frame rate of the 720p movie is a lot higher than the 1080p. And well, 2K is a standard for digital cinema. That's used, in various locations in the Netherlands. You are now getting 2K cinemas, and it gives a pretty nice picture. But that's not enough. We are working mostly with materials as Super HD and 4K. Super HD, if you put 4 HD displays together, you can create a display which can play Super HD content. This is about 6 gigabit per second uncompressed. Compressed, this will be about 500 megabit or something like that. And 4K is a standard we're moving to. And we have some footage recorded in 4K also. Streaming for... Did I miss a slide? No, well, streaming 4K. Okay. It's not working anymore. There are 2 ways to stream 4K. We have the NTT way and the Sage way. NTT uses a JPEG 2000 codec. This requires special hardware made by NTT, and it costs a lot of money to purchase this hardware. So we also have Sage. Sage stands for Scalable Adaptive Graphics Environment. It's built by EVL from the University of Illinois Chicago. and it uses S3 texture compression to compress the video. And the cool thing about this is that we can use normal video cards for decoding these images. Well, we are building a SceneGrid Open Content Exchange. What does the SceneGrid Open Content Exchange do? We are collecting high quality digital media such as HD, SHD, and 4K, of course. We also collect audio, which we also play during the movie. Stereo, 5.1 sound, 7.1 sound, and much higher. We have some. There are a couple of nodes in the world. One is in Tokyo. The other one is in San Diego, and we at the UVA have one node. The function of a Coke is to distribute movies to different members of the community. This must be done securely, so we are using traffic separation to facilitate this, like VLANs or dedicated links. A Coke should also support testbeds for transcoding of movies, management of the content, preservation, so the storage of the content, and of course the distribution. Good. We have a picture here of what we're trying to build. It's an RDF describing infrastructure. RDF stands for Research Documentation Description Framework. At one side we have, at the left side we have a storage node. That's the green blob. The content is over there, and we want to stream content to the to the display at the right side of the screen. The user doesn't want to know about the underlying concept, so the user wants to have a portal for like YouTube or SuperTube, and he wants to click on a movie, and he wants to say, I want to see it on this screen. Well, the network has to do has to have some intelligence. So we use RDF to describe the content, the resources we got. We use NDL to describe the network topology, and so we can, for example, play a movie. If some user wants to play a movie on a certain screen, we can, if we have the content, we can re-encode it to another format and put it to the screen. Well, our code currently looks like this. We have the DUS3 cluster, which has a lot of computing power, which is connected with a photonic switch to our storage nodes. It uses 2 times 48 terabyte storage. We have the Remnant cluster, which we can also use to do some experiments. Of course, a streaming node to stream the video. And this is all connected to a photonic switch, which has some connections to Netherlight, SurfNet, but also connections to our Nortel PBT testbed. Okay, to facilitate the code, we must build a media network with the following properties. Multi-domain. SceneGrid is an international organization with a lot of different companies. So, it has to be able to communicate multi-domain. It has to be secure because there are a lot of companies, because if you, for example, distribute films like from Lucasfilm or something like that, the companies don't want to get it into the wrong hands. So we have to use we have to look at traffic separation very carefully. It has to be high bandwidth. As you could see on a few slides before, uncompressed stream of 4K is roughly 7.6 gigabit. So that's quite high. And at the lowest, we have to use 1 gig interfaces to use for compressed movie. It has to be flexible. If we want to set up links to, sometimes want to set up links to display directly, or sometimes it has to be computed on re-encoded on a storage cluster. So those links should be set up dynamically, or not very fast, but fast. And the links should be deterministic. We currently use photonic links at the UVA. Starplane is a project who is working on that. But mainly we use SONET circuits and Ethernet VLANs for this kind of links. And we are looking into PBT or PBB-TE as a next step in the distribution. Okay, an overview of PBT. PBT stands for Provided Backbone Transport. It's also called PBB-TE. It provides deterministic point-of-point links on an Ethernet level. PBB is also known as Mac-in-Mac. It encapsulates Ethernet frames inside other Ethernet frames, which are used by the carrier network. So that's where you have the separation of customer traffic and carrier traffic. PBT also extends PBB by using a connection-oriented approach. So you actually disable MAC learning on the switches. So every switch has to agree in setting up a connection like that. We are adding connectivity fault management. So if a link breaks, it will be noticed, and eventually a backup path will be used. We use traffic engineering, and there is some Ethernet OEM. Which, of course, reports on lost frames and or delayed frames and generates alerts if needed. More info about the underlying concepts, you can. If you want more info about the underlying concepts, you can go to the talk about PLSB on Thursday. It will be given by Gerard Jacobs from Nortel. The benefits of PBT. Well, traffic engineering links provide deterministic connections. So that's for Cinegrid that's important, because if there is some link problems, we will see that in the movie. Connectivity monitoring gives detailed statistics about and detects broken links. This can come in handy sometimes. Link protection provide a backup path when the primary path fails. We actually it could be useful if the failover mechanism is fast enough, but more on that later. And of course, compatibility with regular Ethernet hardware allows an easy integration in existing networks. So you can reuse old Ethernet switches and use them in this network. But you have to be careful because they don't participate in the traffic engineering scheme of PBT. So you have to do traffic engineering on those switches yourself. The scalable approach makes PBT future-proof. Well, what we are going to focus on is mainly traffic engineering. As I said before, it are large streams, and 4K streams are very, very fragile. But also scalability, flexibility, Ethernet compatibility, and multi-domain aspects are some important factors we should consider. So, we have some open questions. 4K streams are very fragile. Is the quality of service good enough to facilitate 4K video streams? Is the 50 millisecond failover time between a primary path and a backup path small enough to keep the stream running? Or should we tune it and use a smaller failover time, which brings some other problems, of course? And can we somehow talk to the equipment to set up paths using our own software? Well, this is our PBT testbed. It has some QuickTime problems, but we have 3 Metro Ethernet switches from Nortel. The green line is a Cinegrid stream, a movie stream, and we do some traffic generation, and we try to fill up the links on the switches, and we do that as well with normal VLANs as with PBT VLANs, and we try to see if the stream gets disturbed. Well, our roadmap. We have to connect the testbed network to our Cinegrid environment. So that's the Coke I was talking about. We should do performance tests with and without PBT enabled. And if that works fine, we have to look into multi-domain and try to use regular switches on the links and try to use hybrid paths, so we can use PBT. We first can use PBT, then go to photonic, and then back to PBT or something like that. And of course, we have to look into provide a link state bridging, which is a way to define point to multipoint links and to a bit of layer 2 multicast onto the network. Geert Jacobs is going to talk about this tomorrow. Well, questions?
Questions, comments? Yes, there is a question.
You didn't mention about the video compression. I understand that every test has been made with the video without any kind of compression.
Can you repeat it, please?
Did you use video compression in your?
Yeah, we use some video compression, mostly JPEG 2000. That's used for the big streams.
What is the bandwidth then?
The bandwidth then is below around 500 kilobyte per second. So you can carry that on a 1 gig link.
Okay. Any other questions? I was wondering, what is the time frame for your work? When we can expect some new developments? I'm hoping I'm preparing a demo for supercomputing at the end of this year, and we are trying to use some multi-domain aspects in that. So, yeah, it's going pretty fast. Pretty soon. Okay. Pretty soon. Any more questions, maybe? No? Okay. Thank you. Okay. Thanks. And we have come to the third presenter of our session. Let me present Damien Marshall. He's from University of Amsterdam, where he's doing his postdoc. He received the PhD from University of Lille, and he's a specialist in computer graphics and computer animations. But the topic is more related with grids, and EVLBI software correlation. So, floor is yours, and explain us what it is all about.
Yes, okay. Excuse me, do you have a ladder pointer? Maybe this could help me. Okay,
maybe
but
you can start, and then
yeah, I
will
will
get the
start.
pointer.
Okay, so I am Damien Marchal. This presentation will be about the SCARI project. The SCARI project is a joint project between the Jive Institute, so Joint Institute for VLBI in Europe, the University of Amsterdam, and the SARA, Center for Supercomputing and Networking. Okay, what is SCARI? SCARI? In the SCARI project, we want to make a software correlator for VLBI on top of grid middleware and infrastructures. Here is the outline of my talk. I will first make a quick introduction about radio astronomy, what is VLBI, what is EVLBI, what is correlation. Then I will present you what is more specific to the SCARI project, so software correlation. And finally, I will describe you some experiment we are doing using the DAS3 Dutch grid and Starplane. Let's go. In radio astronomy, basically what we are doing is observing the sky into the radio frequency domain. Here is just illustration showing the same pieces of the same part of the sky, but with different frequencies. So, very important parameters when doing a radio astronomical experiment is the size of the dish. The radio telescope dish. And the larger is this radio telescope dish, the higher is your angular resolution. Here is just a picture of the Arecibo radio telescope. It's 300 meters diameters. And I think, but in general, it's considered as relatively hard to make a radio telescope larger than 100 meters diameters. So to overcome this limitation, there is a technique called aperture synthesis imaging, in which instead of using a very big radio telescope to get a very high resolution picture, you combine the signal of multiple ones, and you get a much improved picture of the sky. That's why we are used to see this kind of array of telescopes. This one is in Westerbork in the Netherlands, and this one is the VLE in US. But now the important parameter is not anymore the size of the dish. It becomes to be the distance separating two radio telescopes. Basically, the more the telescopes are far away, the higher is the angular resolution of the picture you can get. Here come VLBI for very large baseline interferometry. In VLBI, the idea is to have telescope located all around Earth and recording the signal coming from the space, and store it on tapes and send it to a central place where the signal is processed in order to generate the final picture. Okay, here's a different view of the data flow. We have the radio telescope. Currently, VLBI experiments consist in storing the data gathered by the radio telescope, and then this data stored on a disk or on tapes in the past are then sent to an Ardoise correlator, which is a very supercomputer made specifically for correlating data. And Jive, for example, is operating such kind of correlator. And currently the data transfer is done by planes and trucks. And there is a second pass, this one, which is called EVLBI, in which the radio telescope is directly streaming through computer network to the Ardoise correlator. On this picture, you can see all the radio telescope participating into the Express project. I invite you to the plenary talk of tomorrow from the director of Jive. There will be even a demo of real-time correlation between some of these telescopes directly streaming the data to the network up to the Netherlands, so here, up to the Ardoise correlator. So now the SCARI project. In the SCARI project, what we are trying to do is, our starting point was that currently grids are more and more efficient, the network is also more and more efficient. And so it starts to be interesting to see if we can replace the hardware correlator, which is a relatively complex piece of specifically made hardware, by a complete software implementation of the correlation. So this is what we are trying to achieve into the SCARI project. Few arguments of the interest of having a software correlator. The first interesting point is that it's much more flexible. It's much more flexible in two aspects. The first aspect is that with a software correlator, you can change the algorithm. You can tune it for specific experiment. While on a hardware correlator, you have to rebuild a new hardware if you want to make specific experiment. But it also have a different flexibility aspect, is that you can run it everywhere. You can just take the software and run it on a grid that is relatively close to the radio telescope, instead of sending all the data to the other part of the Earth, to the central hardware correlator. You can send the correlator close to the radio telescope. So this is the advantages of software correlation. The major drawback is that software correlation is much less efficient. I will show you a few slides later. So, but here is the design of the software correlator. It's quite a traditional approach. It's based on, we have the radio telescope. They are streaming the data to a set of input nodes. These input nodes pre-process the data. The main two pre-process steps are consist in cutting the signal in different subfrequency band that could be correlated individually, and also to cut the signal in the time domain into little chunk of time. And these chunk of time slice are then sent to the correlator, to the correlation nodes that do the correlation step for you. And finally, the output node just gather the result of the computation. Here we can see that the input flow is equal to the output flow around an input node. It's also interesting to see that the output flow after correlation is nearly nothing compared to the input flow. In our current experiment that we are conducting, we are considering that we have 4 data sources for a radio telescope or dist streaming the data, and each of these radio telescope is streaming at 256 megabytes per second. This is what the hardware correlator can currently do. So it can handle 16 radio telescope at 1 gigabit speed. So it's much faster than the software correlator. And this is what is expected for future EVLBI experiment and operation. Okay, so we can identify 2 kinds of data flow. The first one is between the radio telescope to the nodes. It's something like point-to-point fat pipes over very long distance, while these links are more shorter distance and also with a much reduced latency. What makes the SCARI project also very interesting from a scientific point of view is that it should operate in both batch correlation mode or into a real-time correlation mode. Into batch correlation, the idea is that we have the data that have been gathered from the radio telescope stored on disks, and then we can correlate when we have time. So this means that if we don't have enough network resources, or if the network throughput changes even dramatically, this will just impact the speed of the processing. This is really a completely different setup if we are in case of real-time correlation. In case of real-time correlation, the radio telescope are directly connected to the software correlator. This means that if the network change in between, if the throughput drop, if the number of nodes and the resource power drop, this will impact the success of the observation. Basically, we can see that batch correlation is a matter of fastness, how much you will wait to get your result, while real-time correlation is more something linked to reliability of the link you use to feed the correlator with the input data. And so all the networking quality of service system. if you are interested, we will be pleased to do some demo on the demo booth tomorrow. Oh, okay. So, what are we supposed to do with the? Oh, okay. So it worked. So now let's speak about our experiment using the Dutch Grid DAS3. We wanted to evaluate first the scalability of the software correlation, its performance aspect. We also wanted to evaluate the DAS3 network capability. I will describe a bit more the DAS3 network, and also evaluate what is called bandwidth on demand services. So DAS3 is a Dutch grid. It was made for a researcher to do experiment. It's composed of 5 clusters located at in different cities of the Netherlands. Each node in one cluster has a 1 GiG network interface and a 10 gig MirrorNet interface. And all the clusters are connected through a fast interconnection network that is managed by an entity called Starplane. The idea of Starplane is that an application, in order to use this fast interconnection network, when an application wants to send data from one cluster to a second cluster, the application has to request the right to use this fast interconnection network, and this can go through 2 kind of interface. One is, I would say, the official interface, which means you go procedurally, so your application has to request the networking resources with something like get path, cluster source, cluster destination, starting time, duration of the experiment. This is also close to what we can see in DRAC, for example, to dynamically request a lie path between 2 endpoints. Or it can also go through a kind of declarative syntax, a kind of query languages that allow to build more complex queries, which mean you can ask for a path between an unknown location to Leiden, it's a city, and a second path to the same unknown location and a different city. So this permits to build some kind of graph topologies, application topologies with unknown in it. And then you can check availability, reserve, and then deploy your application and use it. So the first test we made was to test the efficiency of the cluster-to-cluster data transmission. The way we did it was to make an application transmitting data from one cluster to another, and this application used the normal socket API and a middleware to hijack the socket API, and will query Starplane management plane, and if a path is available, the middleware will redirect the traffic from the normal 1 gig network to the 10 gig interconnection network. So basically here is what we can easily have on DAS3 and Starplane. Here is the application application A and B are executed. Application A started. We can see it's using the 1 GiG network, so it's relatively slow. Here we can see the 2 applications are sharing the same bandwidth. And after some time, we can see here that the application have received the right to access to the fast interconnection network, so 10 gigabit lie path, and then all its traffic is switched, and we can achieve much better bandwidth. So we have enough bandwidth to transmit data between the input nodes to the correlation nodes. Yeah, this is what I want to say here. When you have a distributed application on one end, it has its own topology, its own networking topology. And all the challenge consists in how can we map this complex and application-specific topology to the topology of the underlying resource we have. So the way the way it happens in SCARI now is that the nodes here are allocated to the different clusters. The input nodes are sticked to the University of Amsterdam, and between University of Amsterdam and the other cluster on which node have been acquired, there is a light path allocated through star plane. Currently, the data sources, so the radio telescope, are located close to the input nodes, but we are planning soon for a test bed in which we have the radio telescope or the data sources, put it all around Europe, streaming the data up to the input nodes. And we would like to have this path protected or with quality of service enabled. So here's just the query I used for this deployment. So I ask for the UVA cluster for 2 unknown cluster. I want 100 nodes. I want these 100 nodes to be allocated at UVA C2, C3, which are free variables. And then we ask for paths between UVA C2, UVA C3, and we reserve everything, and we can start and run the application. So the result of these things, first on the performances aspect. The first result we get here is that the input nodes, you remember the nodes that handle the traffic received from the radio telescope that do the pre-processing, can handle relatively easily, or not easily, but we have good idea on how to reach this 1 gigabit data flow, input flow, and streaming 1 gigabit output flow. What the second performances result we got from our runtime experiment on DAS3 is that we, to do this 4x 256 megabyte observation or experiment, we probably, we need something around 100 correlation nodes. So this means we will need a lot of number of computers to make something that is relatively little compared to what the hardware correlator can do. And this is much more than our theoretical estimation. So this means the next step will be to see how we can use a much higher number of nodes by joining multiple clusters, multiple completely separated grids, which means we will need between these grids to be able to set up also secure path between them. And then here is more just the result to show you the result of correlation. This is what makes sense for astronomers, basically. And in our future plan, what we wanted to achieve soon is that we want to have a secure connection between the data sources to the input nodes. And as the software correlator can be executed everywhere, this means that we should be able to build this path dynamically. That's why we are trying to work with the Géant 2 Autobahn project to provide us the path. But currently, we can have this path, and we are still missing the last 200 meter, which is, I think, a standard problem in a lot of projects. So, this is also something we would like to have happen, but not from the SCARI point of view, more from a kind of user of grids point of view. We would like to be able to be as much abstracted from the underlying infrastructure as we can. And we think this should go through this kind of querying interface. Basically, you describe your application through the query, and then the resource allocation of the grids, allocating nodes and network, will do the resource allocation for you. So you don't need to do manual things by yourself. So here's this kind of query we dream about. So the capability to ask for paths between an unknown cluster and some known radio telescope location, asking for nodes, and then asking for also paths between the different computation resources, basically to have the application executed in a secure environment in which everything should be controlled. So I can, oh no, I was supposed to skip this one. Okay, so just one of the main conclusion I wanted to say today is that I have seen a lot of presentation on it. We can do a lot of things at the networking level. We have fast enough network. If you look at the specification from a new router, you see a huge amount of services. But and on the application side, we have a lot of requests. And I think it was said yesterday this way, is that the middleware in between doesn't allow as much as we want as user or as we could as a network provider. There is a lot of features on the networking hardware that are not yet exposed through the middleware to the application. And this is something we would like to happen. And this will permit, from the application point of view, to stay focused on the what we want to do and not how we do it. So now, just a few comments on this slide because it's not going over. To conclude, yes, we can do software correlation. What I call cost is that we are yet consuming a lot of resources to make something that an hardware correlator can do for a much reduced cost. So that's why we want to investigate more heterogeneous or hybrid architecture consisting in delegating some computation to GPU FPGAs. So this is something that should happen to improve the performances of the application. This is the end of my talk. I would like to thank all my colleagues at UVA and Jive, from whom I grabbed a lot of slides. And thank you for your attention. So if you have any questions, feel free to ask.
Thank you. So, questions? Comments? Forest of hands? Well, I think it's an interesting and challenging project. We've heard about those radio telescopes in the context of many presentations, and this is just another aspect where we can see that they need those last 200 meters which you mentioned to make it more efficient and faster. So I wish success with your work, and thanks for your presentation. Let's applaud again. Thanks for coming. This brings us to the end of the session a little bit sooner, so we can be the first ones to get the coffee. I would like to remind you about the evaluation forms. They are accessible online. Please mark those presentations you liked most and those you didn't like so much. Today, after the conference at 6 o'clock, there are a few BOFs. Information about them are in these slides that are running between the sessions. So please take a look. If you are interested in any of those topics, please join. And time for coffee.